Our next speaker comes from RUAG Aerospace. RUAG Aerospace is incorporating additive manufacturing into the manufacture of satellites to aim for lower costs and improved characteristics. He is the technology expert with a master's in science and aviation. Ladies and gentlemen, Manuel Aliprandi. Round of applause, please. Yes.
So, good morning everybody, also from my side. My name is Manuel Aliprandi, as said. Today I want to show you what our vision and what our idea is of how to incorporate additive manufacturing into the manufacturing of satellite structures. Just to introduce shortly RUAG Space. So RUAG Space is part of the RUAG group, which has roughly 9,200 employees all over the world. So in RUAG Space we are 1,200 employees. As per today we have 1,000 and more parts successfully delivered to space. Basically our company is split into 3 product groups, which is one electronics, where we do electronics for satellites, so for spacecraft. We do our second product group is launchers. In launchers we do basically the payload fairing for the Vega as well as for the Ariane and for different US launchers. And the last group is the product group spacecraft, where we do thermal insulation systems as well as spacecraft structures. And now we will focus on how we include additive manufacturing in spacecraft structures in order to be more cost efficient and to have better characteristics. So the first question which arises at the beginning is, why should we use AM in space? So what we developed is we have always 2 aspects which we should cover, which one is the programmatic aspects and one is the performance aspect. So with today we are able to cope with these 2 aspects with additive manufacturing. For the performance aspect we can allow more complex design, we can integrate functions and we can increase simply the performance of the parts. And the programmatic aspects, we are very flexible, we can decrease cost and we can optimize the supply chain. So one might think that these 2 aspects are completely decoupled one from each other, but actually they are not. So with a more complex design we are more flexible because we can adapt to late inputs for our customer in our design. If we integrate the design, we can really go down with the cost because we have less parts which are to be manufactured and less parts which are to be integrated. Also with the performance, if we decrease the mass of our parts, we can increase the payload of a spacecraft, meaning that we can carry more instruments, we can carry more equipment up to space. So how can we reach these aspects? What we can do is we have really to take the technology and push it to the boundaries. What you can see in the picture is one of our recent projects, which was the LEROS project. It was part of so basically it was the engine support structure for the SpaceIL spacecraft, which was launched just a month ago with to the moon. So it was intended to land to the moon. It did arrive there, not quite successful, so it crashed, but not because of our part. So for us, still it was already a success. So you can see on basically on the orange part, so this orange picture was the original part. You can see that there was one big part missing, which is the central of the additive manufactured part. So it was the heat shield. What we did, we integrated the heat shield to be part of the structure in order to reduce an additional part and in order to have a multifunction of these parts, meaning structural and thermal. With this, we were able to reduce the mass of the part by 25%, and we were able from the beginning on, starting with an optimized design, to be in a certain frequency range which was requested from a customer. And the size of the part is roughly 700 millimeters in diameter, so it's already a very big structure. So the question which is how can we go to push to the boundaries these technologies, and it all comes from the design. So we really have to understand the holistic approach. We need to understand from the beginning to the end what is the need of our parts, and not only of the parts but of the whole system. So you see already at the beginning with additive manufacturing we can focus on the performances, we focus on the requirements, but we can also focus on cost and we can focus on schedule. which is not so easy on big assemblies to be done with conventional design. So you can see that the whole chain is basically one flow. There is no cycle which comes back, which would be with conventional design, where we have a design, we have an analyze, we see if the part works. Most probably after the first cycle it does not, and then we have to redesign. While with additive manufacturing, we are able to optimize or use optimization software in order to go to our goal from the first time on. And afterwards, we can simply test and qualify our components. What is also now a game changer in the world of spacecraft is the cost. We have seen with, for example, OneWeb, where we also deliver some part of the structure, so basically all panels. The cost of these panels is a fraction of what it was or what it would be for a conventional design. And additive manufacturing allows us to go even more deep into this. So on the left side, you can see an original part which was part of the payload fairing where the spacecraft is attached to. And the original part was 23 parts. You can see only one there. And we optimized this using additive manufacturing to have, instead of 23 parts, only one. The cost of the parts was 40% less. The stiffness was increased by 30%, and the lead time was by far shorter than for the original part. Also, we should not only think about design, we should also think about how can we implement different materials, how can we think out of the scope to not use our standard metals as we were used to in the past. So on the right side, you can see a vent port, which is also attached on one of the payload fairing, which ensures the flow of the air from the inner of the payload fairing to the outer atmosphere when the rocket is launched to space. So basically what we did, we optimized the design in order to have less components, but what we also did, we changed the material. Before the part in the middle, the black part is a flap. The flap just opens when the part is launched to space. So what we have done, we exchanged it by a polymer part, simply because it was not needed to do it in metal. But as we do not really have serious production in our business, a polymer part would never be able, so we would never have been able to do that in polymer part with conventional design. So what is also very important for us is to be agile. Why? Because we as structure developers, we are quite late in the chain of getting the input, but we need to be quite flexible. And so here you can see an example of how we delivered a bracket antenna for Earth observation, and the whole project was 8 weeks. So from kickoff to the part finally mounted on the spacecraft was only 8 weeks, with full qualification and all. And the part is now flying, so we even have flight heritage within this part. So for us, this to be agile is so important, because the structure is mostly the last one who gets the input of the design, because first all equipment, all instruments are designed, and afterwards the structure is defined. But we are the first one which are needed when it comes up to integration. So for us, with additive manufacturing, we can be really flexible, and we can also mitigate the risk, because at very late design, we can still change our design. So what the vision of us is to really rethink the way of designing additive manufacturing. You can see different components which are already designed in additive manufacturing. You see, for example, honeycomb cells from Fraunhofer Institute, or from Thermacore, which try to implement heat pipes within additive manufactured parts. And you can see some of our inserts, which are block inserts bonded into sandwich panels, made out of the additive manufacturing to be able to cope more functions. But what we also see is that design for RM, so taking one component or even a small sub-assembly, it is successful because you can have less costs, you can have increased performances, but it's only a one brick in the wall. It's only the beginning. What we really should do is to understand the system approach. So as you see per today, this is one of the Sentinel spacecraft where we did the structure. It's as every other spacecraft, it's a box made out of sandwich panel. But how can we use additive manufacturing so we could understand the whole system and go into the future, which would be that we completely redefine the way on how to use additive manufacturing and how to design spacecraft. So to do so, what we have to do, we first have to understand the mission. So we have to know what is really needed. We have to understand the function of the parts which are needed to achieve the mission, and afterwards we can set the requirements. Requirements can be in geometry, it can be in strength, so we have to define these steps, but from the beginning on of the design, we have to think about additive manufacturing. And in order with this, so the vision would be to really create a multifunctional system, which could be a spacecraft, which could be part of the launcher, which could be maybe an entire launcher. As a last point, I want just to also give the idea what we have within our company on how should we implement the thinking of design for additive manufacturing within our company. We're often seen, and also we started at the beginning, to have a couple of people which performed kind of a center of excellence or AMC or center of competence or however you want to call it. But it's only limited to a few people which are able to perform tasks within additive manufacturing. What we see today, which is the might better solution, is to have a fully embedded system. So to have people which are usually designing spacecraft, but everybody should be aware of additive manufacturing, because it is not only a technology for manufacturing, but it is also a way on how to design the parts. So if everybody is aware of this technology, you can put the boundaries more, so you can push the technology to the boundaries and you can make the most use out of the parts. So in the end, I want to conclude with what is the lessons learned that we had in the last 7-8 years that we are working with additive manufacturing for spacecraft. So the first is that, yes, we have already achieved a lot, but we are still at the beginning. It does not only mean for the companies manufacturing the parts itself, but it's also for us as design authority. What we also see is that we have to understand the process and the material. Again, process is also linked to the design. Also, we have to increase the collaboration between industry and academia, because academia is doing a lot of research, but it's very difficult to get it into industry as per today. Also, we have to facilitate the exchange between the AM community. So companies are working on the same solution, but why shouldn't we all put together our results and make the most use out of it? And in the end, we should also explore more new methodologies and technologies in order to be able to maybe redefine the complete design of additive manufacturing. And as a last point, what is our vision or what is our idea is that we should not think about additive manufacturing, about this layer-to-layer process to be a problem and to be an issue, but we should see that there is a chance to use it. So thank you very much for your attention.